Okay, perfect. So hello, everyone, and welcome to today's SEDS Online webinar. As always, we'd like to thank our sponsors with IAS, which allow us to offer all of these great resources free of charge, which Amy and I were just talking about. This includes the recorded lectures, some of our learning tools, and even virtual field trips. So make sure you take a look at our website to see all the new info. So today's lecture is by Amy Hsu, who is a sedimentologist at Simon Fraser University. She is currently doing her PhD, and her research interests include assessing paleoclimate cyclicity using Miocene and Pliocene sedimentary records to refine future projections of tropical cyclone frequencies, intensities, and climate change. So thank you very much, Amy, for coming today, and I'll hand it over to you.
Thanks so much, Simone. Should I just start sharing my screen?
Yeah, for sure.
Okay. All right, hopefully everybody can see this.
Yeah, looks good.
Okay. So just give me 1 second. It's been, 3 years using Zoom, and I'm still having some issues figuring things out. All right, there we go. Okay, so hello everybody. Thank you so much for attending today, and thanks to everybody at SEDS Online for hosting me. So as Simona mentioned today, I just want to share some of the work that I've done for my PhD over the last few years. And the main purpose of my research is to understand how the evolution of a rapidly uplifting orogen might influence the preservation of different climate signals in shallow marine strata at different stages of its growth. So as we all know, Earth is rapidly warming in the present day due to an exponential rise in greenhouse gas emissions. And we really need to understand how extreme weather events like tropical cyclones and monsoons are going to respond to the warming climate. And many climate reconstructions are based on quaternary data, but global temperatures during this time were actually relatively cool. And this is us in the orange line here. And we really need to understand the impacts under global warming. And the last time that these conditions occurred was in the Pliocene, where temperatures are around 3 to 4 degrees warmer than the pre-industrial period, and carbon dioxide concentrations exceeded 400 parts per million. So this makes the Pliocene climate a good analog for near future Earth. And one of the reasons why Earth's climate was warmer in the past was due to its position around the sun, described by eccentricity, or the shape of Earth's orbit around the sun, precession, or the wobble of Earth's axis, and obliquity, or the tilt of Earth's axis. And each of these parameters have different frequencies. Long eccentricity completes a cycle every 405,000 years, and short eccentricity around every 100,000 years, obliquity every 41,000 years, and precession around every 20,000 years. And traditionally, studies on these cycles and their impact on climate and deep time have been conducted using proxies from deep sea and lakes, where sediment continuously accumulates. And this is thought to provide a complete record of environmental change over time. However, sediment deposited in these environments are indirectly affected by climate-driven processes like sea level change or intensified extreme weather events. Records from the shallow marine environment, on the other hand, are directly impacted by climate change. However, they're usually overlooked as climate archives because sediment are commonly reworked by said extreme weather events, and this results in an incomplete record. So this is a neat animation that demonstrates how sediment is preserved or not preserved in a typical shallow marine setting. So here we have elevation on the y-axis, which we can consider as accretion of sediment, and basin subsidence. And then this is over time in years on the x-axis. And we can see that only a small fraction of the sediment that is deposited is preserved, and this is shown by the blue. But the record is largely made up of gaps and reworked sediment, shown by the red and the gray. And the only way to overcome these gaps in the record is if the basin accommodation space and sedimentation rates are sufficiently high. And a setting that meets both the criteria of being high accommodation, high sedimentation is the Western Foreland Basin of Taiwan. And Taiwan was formed by the collision between the Eurasian plate and the Philippine Sea plate, and it began approximately 6.5 million years ago. And this formed the Guizhou Formation, which consists of the lower Guangdao sandstone, the middle Shilofin shale, and the upper Yutengping sandstone. Recent studies of the Western Foreland Basin have found evidence of past climate signals preserved in the rock record. So Dashgard et al. In 2020 discovered tropical cyclone deposits in an outcrop of the Guizhou Formation. The tropical cyclone deposits are characterized by trough cross stratified sandstones indicating changing flow directions. And this is overlain by hummocky cross stratified sandstone. And we see that there is mud rip-up clasts interspersed throughout the sandstone, and all of it is capped by more mudstone. So all of this is evidence for high energy deposition with a high concentration of suspended sediment, which is what we'd expect to see with sediment deposited by a tropical cyclone. And just to know that these are examples of exceptionally preserved tropical cyclone beds, but in reality, many beds don't manifest this way. And a study by Vaucher et al. In 2021 found that precession-driven climate change are well preserved in cycles of mudstone and sandstone of the Pleistocene shoreline formation in the Western Foreland Basin. But what we're really interested is the Pliocene, and we also want to understand how the shallow marine strata of the Western Foreland Basin evolved as a climate archive before and after the emergence of Taiwan. So this leads me to the rationale for the first part of my study, which is to evaluate how the growth of Taiwan influenced sedimentation to the adjacent shallow marine basin during a time in Earth's history where climate was warmer than today. So as I mentioned before, Taiwan is situated on a collision zone, and therefore it's very tectonically active. And for example, these are some photos that demonstrate the amount of damage created by the Jiji earthquake in September 1999. And this was a magnitude 7.3 earthquake that created over 130 landslides. It displays a nearby dam upwards by 9 meters, and it created waterfalls in the river channel. These frequent earthquakes and mass wasting events liberate an enormous amount of sediment, which is then transported to the adjacent seas by the steep rivers of Taiwan. And the ability of these rivers to transport large volumes of sediment is dependent on precipitation. And in Taiwan, there are basically two main processes that deliver precipitation. And first, Taiwan experiences frequent tropical cyclones, which account for almost half of the annual rainfall in Taiwan. So this figure shows the tropical cyclone tracks and intensities for the last approximately 150 years, and Taiwan is located right here where many of the category 4 to 5 cyclones pass through. And on average, we see around 3.5 tropical cyclones per year here, and around 1 super tropical cyclone or category 4 to 5 cyclone every 4 years. And second, Taiwan is also impacted by the East Asian summer monsoon every year, which accounts for the other 50% of annual rainfall. So while both of these mechanisms deliver almost all of the rainfall in Taiwan, today around 75% of the sediment from Taiwan is transported to the surrounding seas during tropical cyclones. And this is due to the extremely high winds and torrential rains that occur during tropical cyclones. And this is a video of Typhoon Haikui this summer, which passed over southern Taiwan. And you can see just how strong these winds are and how much precipitation there is. And here is an example of what the rivers look like after a tropical cyclone. So you can see that it is completely overflowing and full of sediment. And you can throw in an odd bridge in there as well. So these videos just give you an idea of how powerful these events can be. Now, in the northern hemisphere, where Taiwan is, tropical cyclones follow a clockwise path. So this means that the cyclones initiate over open water, they move over across the island, eroding sediment as it goes, and then back towards the ocean. Therefore, the geochemistry and mineralogy of sediment deposited in the Taiwan Strait today largely reflects the Taiwan source. And in the Paleo-Taiwan Strait, or the Western Foreland Basin, it was thought that sediment contribution from Taiwan didn't begin until the early Pleistocene and possibly the late Pliocene. However, the uplift of Taiwan began in the late Miocene. And back in the late Miocene to early Pliocene, the climate was also warmer, so there should have been more frequent and stronger tropical cyclones, which would have increased sediment export from Taiwan to the basin. So this shift in sediment source to the adjacent basin should also have occurred sometime in the late Miocene. And to confirm this and to understand how sediment sources to the Western Foreland Basin evolved through time, I logged a 430-meter-long outcrop section of the Guizhou Formation in northwestern Taiwan along the Dian River. And from this outcrop, I took samples to analyze for clay mineralogy, delta carbon-13 and carbon-nitrogen geochemistry, and rock magnetic susceptibility. The first proxy that I decided to look at is clay mineralogy. And the reason why I chose to analyze for clay minerals is because they can provide insight about a wide spectrum of environmental changes, which can all be used to deduce how the clays formed and where they came from. So for example, this ternary diagram that you see here shows the proportions of different clay minerals from modern day fluvial sediments sourced from Eurasia in gray, Taiwan in green, and the Philippines in purple. Modern day clay delivered by Taiwanese rivers are dominated by illite and chlorite, indicating a high degree of physical weathering. While clays from the Philippines are dominated by smectite, reflecting their volcanic source. And clays from the Eurasian continental margin are richer in kaolinite, which reflects both their metamorphic source terrain and a higher degree of chemical weathering. And in the rock record, I would also expect clay mineralogy to show a distinct signature that reflects the mechanism of weathering and the parent material. And overall, in the samples that I collected from the Guizhou Formation, illite and chlorite account for most of the clay minerals, with variable proportions of kaolinite and smectite. Another way to determine the source of sediments is through the use of organic delta carbon-13 and carbon-nitrogen geochemistry. So marine and terrestrial plants take up nitrogens and different isotopes of carbon in slightly different proportions, and therefore their geochemical makeup can be used to distinguish where the organic material in the sediment formed, either on land or in the sea. So organic material that formed at the ocean tend to settle on the seafloor mainly under fair weather conditions, and they have less negative delta carbon-13 values and lower carbon-nitrogen ratios. Export of terrestrially sourced organic material to the ocean tend to increase under storm conditions with increased precipitation and runoff, and they're characterized by more negative delta carbon-13 values except for seafloor plants and higher carbon-nitrogen ratios. And I also looked at rock magnetic susceptibility to detect changes in sediment source. So variations in magnetic susceptibility can be tied to changes in sedimentation processes like erosion, transport, and deposition. And by extension, this can provide information on where the sediment came from and how they were transported to the basin. And in modern day Taiwan Strait, samples sourced from Western Taiwan have magnetic susceptibility values that are much lower than sediments sourced from northeastern China. And this indicates that sediment from Taiwan contains a much lower concentration of magnetic minerals compared to sediment derived from nearby Eurasia, and therefore can be used to differentiate between the two sources. So looking at all of my data that I've collected for clay mineralogy, carbon-nitrogen geochemistry, and magnetic susceptibility through my outcrop, all the indicators show that two major shifts occurred in the Guizhou Formation. So first near the Guangdong Sandstone Swilfen Shale boundary, and then near the Swilfen Shale boundary, Swilfen Shale and Yutongping Sandstone boundary. So I'll come back to this figure over the next few slides. Okay, so first, prior to the full emergence of Taiwan in the Middle Miocene, sediment delivered to the Western Foreland Basin were largely derived from the Eurasian continent. And these sediments would have had higher proportions of kaolinite due to intensive chemical weathering, a strong marine organic signature due to longer residence times in the ocean, which would increase the input of marine-derived organic material. It would also have higher magnetic susceptibility due to an enrichment of magnetic minerals in the source rocks. And we see this manifested in the Guandaoshan sandstone, where proportions of kaolinite is relatively high while illite is relatively low. The geochemical signature is fully marine and magnetic susceptibility is high. And as Taiwan rose higher above sea level between the Miocene and Pliocene, the rapid rates of uplift and erosion meant that it quickly became a major source of sediment to the Western Foreland Basin. And sediment derived from Taiwan are characterized by a higher proportion of illite due to the intense physical weathering. Marine organic material would decrease due to terrestrial sediment input from the island, as well as shorter residence times from erosion to deposition to burial. And Taiwanese sediment is also depleted in magnetic minerals. And we see this manifested in the Silofin Shale, where proportions of kaolinite abruptly drops while illite increases. Marine organic material also begins to decrease slightly. And finally, in the early Pliocene, as rapid uplift and erosion of Taiwan continued, it became the overwhelmingly dominant sediment source to the Western Foreland Basin. And this is reflected in the Yutongping sandstone, where organic material delivered to the basin is now essentially 100% terrestrial. And we also used a simple isotope mixing equation to semi-quantify the amount of organic material in the sediment and how much of it came from marine sources versus terrestrial sources. And the results confirmed that in the Guandaoshan sandstone, it had the highest percentage of marine organic matter, which decreases dramatically through the Silofin Shale and then essentially drops to zero in the Yutongping sandstone, with the exception of a few outliers. And the magnetic susceptibility decreased drastically as well due to dilution by an influx of non-magnetic sediment from Taiwan. So in summary, our results show that soon after Taiwan emerged from the Pacific Ocean, it rapidly became a major source of sediment to the Western Foreland Basin at the Miocene-Pliocene boundary, which is approximately 2 million years earlier than previously thought. And then in the early Pliocene, just under 1 million years, sediment supply from Taiwan overwhelmed contributions from Eurasia, and it became the dominant source to the Western Foreland Basin. And this huge influx of sediment was likely delivered by more intense tropical cyclones and monsoons in the Pliocene. And at low latitudes, these processes are affected by the intensity of summer insolation, which is driven by precession. So theoretically, given that sediment in the Western Foreland Basin is sourced from Taiwan and delivered by precession-driven processes, we should expect orbital cycles to be preserved in the strata of the Western Foreland Basin. So this leads me to the second part of my research, which is to test whether orbital cycles are preserved in the Western Foreland Basin and to evaluate how the preservation of potential climate signals changed with the evolution of a rapidly uplifting orogen. And to understand how the evolution of Taiwan influenced orbital cycles preserved in the rock record, we looked at gamma ray data from the Great Leaf Formation from 2 boreholes. We have HYS1 in pink and TCDPA in blue. But first, we need to know the timing of deposition, and so we developed a magnetostratigraphic framework using samples taken from the Great Leaf Formation outcrop at the Dian River. So here's the litholog of the Dian River outcrop again, and we collected 1-inch diameter rock cores from the outcrop from mud-rich intervals, and the sample locations are shown by the X's. And I measured the samples for their paleopolarities. I also identified index nanofossils from these samples and their corresponding biozonations to constrain the paleopolarities to determine the ages of the strata in the Great Leaf Formation. And we determined that the Great Leaf Formation was deposited from 6.3 to 3.2 million years ago, and the boundary between the Guandaoshan sandstone and the Silofin Shale was dated to 5.4 million years ago, and the boundary between the Silofin Shale and the Yutongping sandstone was dated to 4.9 million years ago. We then used the magnetobiostratigraphic age constraints to correlate the gamma ray data to an astronomically tuned delta oxygen 18 ice volume proxy. And in general, low delta oxygen 18 corresponds to warmer climates and higher values correspond to cooler climates. And just a note, the axis is flipped upside down. High gamma ray values are typical of mudstones dominated strata, and low gamma ray values are typical of sandstone dominated strata. So we tuned the gamma ray data to the delta oxygen 18 record based on the assumption that mudstones tend to form under warm and humid climates, and sandstones are related to cool and dry. And the points used to tie these data sets are shown by these vertical gray lines. So to evaluate how strongly eccentricity, obliquity, and precession show up in the gamma ray records, we filtered out any frequency outside of the cycle that we're looking at so that we can see how each individual orbital cycle is manifested in the gamma ray record. So as before, the pink and blue lines represent the HYS1 and TCDPA gamma ray records. The brown wiggle line that you see here represents the amplitude or the strength of the orbital signal that's preserved in the gamma ray record after we apply the filter. And then this black dashed line represents the upper envelope of the filter signal, which highlights the peaks and the troughs that corresponds to strong and weak orbital signals preserved in the gamma ray record. So this black line, this black dashed line is what we'll focus on. So for the first figure here, it shows the results of the gamma ray after being filtered for the 41,000-year obliquity. And we see fairly strong signals of obliquity being preserved in the Guangdao sandstone, and then it kind of drops off through the Shilofin shale despite there being an increase in obliquity. And it kind of comes back in strength through the Yutongping sandstone. Now, looking at the 100,000-year short eccentricity cycle, we see that the strength of the cycles preserved in both gamma ray records are quite high throughout the interval. But again, we see a slight drop in the strength through the Shilofin shale despite seeing a maximum in eccentricity. And in the Yutongping sandstone, the highs and lows and the amplitudes are generally in agreement with orbital eccentricity, and also between the two locations. And lastly, looking at the 20,000-year cycles, in the Guangdao sandstone, we see that generally the strength of the 20,000-year signal preserved in the gamma ray record is quite low, despite seeing very strong precession during this time period. And again, this signal strength kind of drops off and then flattens out through the Shilofin shale, again, despite there being very strong precession. And then after 4.9 million years, the amplitude increases again, and is actually strongest through the Yutongping sandstone. So now putting everything together, the results show us how this rapidly uplifting orogen influences the preservation of climate cycles. And in the middle Miocene, where Taiwan has just barely started to emerge from the Pacific Ocean, the Taiwan Strait, as we know it today, didn't exist. So sediment was susceptible to reworking by erosive waves from the Pacific Ocean. And higher frequency signals like precession are most likely to be removed. And this results in the low preservation of precession signals while obliquity and eccentricity dominated. And then near the Miocene-Pliocene transition, Taiwan began to rise higher above sea level, and the Western Foreland Basin began to increasingly subside. But preservation of orbital signals is poor. So this is attributed to either low sedimentation rates at deeper water depths, which resulted in cycles being below the resolution of the recording instrument, low sedimentation rates obscuring variations in sediment input, or the cycles just not being visible in the gamma ray proxy due to a lack of contrasting lithology. And then after 4.9 million years ago, the rapid uplift of Taiwan continued, and this resulted in increased sediment flux and increased basin accommodation space, as well as the formation of a semi-sheltered Taiwan Strait that shielded the Western Foreland Basin from erosive waves of the Pacific. So unsurprisingly, not only do we see obliquity and eccentricity come back in strength, we also see enhanced preservation of precession signals. So in summary, the study shows that emergence and erosion of Taiwan resulted in increased sediment influx and basic accommodation space and the formation of a semi-sheltered strait, all of which enhance the preservation of different climate cycles. So my next question is, what was the extent of the influence of Taiwan's orogenesis? I want to know if it had the potential to alter sediment records in the deep ocean far out into the South China Sea. So the South China Sea is characterized by complex atmospheric and ocean circulation patterns, which make it an area of great interest for studying changes in the climate system, specifically the East Asian summer monsoon. And changes in the East Asian summer monsoon through time have been interpreted using proxies from sediment cores. However, the South China Sea is situated in a tectonically active area and receives huge volumes of sediment each year from various sources. And these sources have changed through time, sometimes independently of climate, and they can contribute to variations in sediment proxies that might be misinterpreted to reflect climate change. And one of the biggest contributors of sediment to the South China Sea is Taiwan. And this island, which accounts for less than 1% of Earth's surface, delivers around the same amount of sediment each year as the continental United States. So what I want to know is if and how did the evolution of Taiwan impact South China Sea monsoon proxies? And to do this, I looked at 3 records from the northern, central, and southern South China Sea regions and compared them to the data that we have from the Western Foreland Basin in Taiwan. And the monsoon proxies that I'm looking at are hematite-goethite ratios and magnetic susceptibility, which traditionally are thought to vary dependent on monsoon strength. So hematite forms under arid climates, while goethite forms under humid climates. So decreasing hematite-goethite indicates increasing monsoon strength and vice versa. Magnetic susceptibility is related to the extent of weathering by monsoon precipitation. So higher values indicate stronger summer monsoons and vice versa. But looking at our records, so here we have the northernmost Taiwan record all the way to the southernmost South China Sea record. Their patterns clearly don't match, even though the monsoon should have had a regional effect on all sites. So perhaps there are other non-monsoon related factors that are forcing these changes, like the emergence of Taiwan, for example. So again, going back to this familiar figure, before the emergence of Taiwan in the Middle Miocene, sediment delivered to the South China Sea were largely derived from the Eurasian continent. And if you remember, the sediments are characterized by moderate magnetic susceptibility, high delta carbon 13 values, and also high hematite. Prior to the emergence of modern Taiwan, the South China Sea was also open to the Pacific Ocean. And paleocurrents share the same circulation pattern as the North Pacific subtropical gyre, with a dominant clockwise flow direction. And sediment deposited in the South China Sea during this time would reflect provenance from the Eurasian margin and dispersal by these Paleo-South China Sea currents. And in the glacial formation, this is reflected in the high magnetic susceptibility as well as high delta carbon 13 values. On average, hematite-goethite are high in both the northern and central South China Sea, and magnetic susceptibility is stable, which is consistent with a single dominant Eurasian source. And as Taiwan rose higher above sea level between the Miocene and Pliocene, the rapid rates of uplift and erosion meant that it quickly became the dominant source of low hematite, low magnetic susceptibility, and low delta carbon 13 sediment. The uplift of Taiwan and northwestward migration of Luzon also partially enclosed the South China Sea and created a branch of the Kuroshio Current, as well as deep water bottom currents that enter from the Pacific and bring sediment from Taiwan towards the central South China Sea. And we see this in the Silifan Shale and the Yutongping Sandstone, where magnetic susceptibility and delta carbon 13 begin to gradually decrease and then abruptly drop. The gamma ray data also indicates an influx of sand-dominated material. The hematite goethite from northern South China Sea also decreases, again gradually at first and then rapidly. So all of this indicates an accelerated influx of sediment from Taiwan. The hematite goethite record from central South China Sea, which is over 1,000 kilometers away, shows a lag in its response, probably due to its distance from Taiwan, but it also starts to decrease by the early Pliocene when Taiwan became the dominant source of sediment. But magnetic susceptibility remains largely unchanged, and this may be due to mixing of high and low magnetic sources in the region. In contrast, the southernmost record shows increasing hematite goethite and magnetic susceptibility values. So here, the dominant source of sediment has been the Mekong River since the late Miocene. So the increasing trends is likely reflective of changing monsoon intensities rather than changing sediment sources. And then by 3.2 million years ago, the continued southwest migration of Taiwan and its growth resulted in the formation of the Taiwan warm current, which remobilized some sediment from Taiwan northwards towards the East China Sea. So despite strengthening of deep water currents during the late Pliocene to early Pleistocene, relative sediment input from Taiwan to the wider South China Sea decreased. We also see the hematite goethite values in northern South China Sea especially begin to kind of decrease slightly, which is consistent with a relative decrease in sediment input from Taiwan to the South China Sea, as some of it is remobilized northward towards the East China Sea. And again, in the South China Sea, where the Mekong River has dominated sedimentation since the late Miocene, proxy records show no influence from the Taiwan origin. So in summary, our studies show that soon after Taiwan emerged from the Pacific Ocean, it rapidly became a major sediment source to the Western Foreland Basin near the Miocene-Pliocene boundary, which is around 2 million years earlier than previously thought. It then became the dominant source to the Western Foreland Basin by the early Pliocene. And the rapid uplift and erosion of Taiwan resulted in increased sediment influx and basin accommodation space, and the formation of a semi-sheltered strait, all of which served to enhance the preservation of climate cycles. The emergence of Taiwan also influenced the signals preserved in sediment records in the South China Sea as far as 1,000 kilometers away, which have traditionally been interpreted to reflect changing monsoon intensities. And this emphasizes the need to consider and identify non-climate controlled mechanisms that can drive changes in proxy records in order to accurately reconstruct paleoclimate, especially in tectonically active and geologically diverse regions. So this brings me to the end of my talk. And I just want to say a big thank you to my supervisors, Dr. Shaheen Dashgard and Dr. Ludwig Löwenmark, for their support, as well as all of our collaborators who made all of this possible. Thank you so much for listening.
All right, hello. Thank you very much, Amy. That was really interesting, and you had lots of beautiful figures.
No, thank you.
So just so everyone knows, the chat is now open. So if you have any questions for Amy, please feel free to post them in the chat and we can get her to answer those for you. While we're waiting for some questions from the chat, I have one that I would like to ask. So do we see similar features of the climate signals being preserved in other locations around the world? Or is like the emergence of Taiwan significant to preserving those features?
Off the top of my head, I think in shallow marine settings, there's one other study that was done in a basin in New Zealand, which showed that there was preservation of different orbital cycles in the sedimentary record. But I think that's about it.
Wow, that's
Yeah,
really cool.
I mean,
Really unique.
maybe there are people in the audience that can correct me if I'm wrong, but I don't think there's been a lot of work done in the shallow marine realm.
Very exciting. We're getting lots of thank yous and great talks in the chat. But if anybody else has a question, feel free to post it. Maybe I can think of another one. For the South China Sea paper, did you, or project, did you see that it was a regional effect? And if you went further north, do you think you would see anything?
Um, when I started the project, the focus was mostly in South China Sea, just because that was where the main paleocurrents directions appear to be flowing. But I know that with the formation of the Taiwan warm current, and also in the present day, a lot of sediment is transported northwards. So I'm not 100% sure when exactly that started, but I think it would have been later than the time period that I've been looking at.
Very cool. Maybe that can be your next project.
Yeah,
Looking
maybe.
into that. Right. We have a, sorry, we have a question here from James. And he's asking, did you have the chance to look at provenance signals in sandstones, something like rock fragments or heavy minerals, feldspar varieties? And also, very good talk.
Thank you. Thanks, Jane. I know that there has been work done looking at sandstone and looking at uh, rock fragments, and they generally support our findings. So prior to the uplift of Taiwan, most of the rock fragments reflect a metamorphic source that corresponds to a Eurasian source, and then afterwards we see a lot, I guess, much cleaner sandstone, coarse-rich sandstones that correspond to a Taiwan source. But I'm not sure. I think the only difference is that the age constraints were not as uh, oh, I'm like I've just put my foot in my mouth, if that's saying. I don't want to say they're not as well constrained, but at the time, I don't think there was a age model that was made for that study.
All right, thank you. Here we have another question from Stephen. Fabulous talk, thanks. Truly a massive amount of sediment being dumped here. Maybe I missed it, but is there a significant loading effect going on?
At the time or presently? I'm assuming so. I guess yes. During the time period that I was studying, yes, there was a lot of loading, and then but as more and more sediment were deposited in the basin, eventually it got to a point where it was completely filled. So right now we actually don't see a lot of sediment being preserved in Taiwan Strait. A lot of it is just being transported out towards the north.
Very interesting. All right, we have another question. A great talk, thanks. What were the primary sedimentary environments you looked at? Primarily cyclone deposits?
So the primary environments that I was looking at, it was mostly restricted to shallow marine environments with definitely a lot of storm influence. I'm not sure if we can say, I think I showed a study in the early parts of my slide. I showed different tropical cyclone deposits. So we definitely know that there's a lot of sediment that was deposited under storm conditions, but in terms of actually quantifying individual storms, I'm not sure that we're able to do that.
All right, thank you very much. I think that maybe we will say thank you, and if anybody wants to see the video again or ask more questions, it's going to be up on SEDS Online's website. So feel free to take a look there, and I'm sure you'd be open to email questions that may arise in the future. And
Absolutely.
thank you very much for coming today.
Thanks, everyone.